Hi, I'm Kathy. In this lesson, we're going to look at logarithmic functions and equations. Our specific objectives are the common logarithmic function, solving equations, logarithms with other bases, and general logarithmic equations. Let's start with the definition of a common log. The common logarithm of a positive number x, denoted by log x, is defined by log x equals k if and only if x equals 10 to the k. We say that 10 is the base of the common logarithm. The rest of this says where k is a real number, and then we have a common logarithmic function, f of x equals log x. Well, let's start with this piece of information right here and simplify some logarithms. The common logarithms we want to simplify, first of all, log 100. If you look back at that statement, it would help if we could write this as log 10 squared, because 100 is 10 squared. And the result of this is 2. An important thing to note is that a logarithm is an exponent. If the logarithm is base 10, then the log is equal to the exponent on 10 on the argument of the logarithm. Using that same idea, I can write this next example as log of 10 to the negative 1, which means the result of that, or when it is evaluated or simplified, we get the exponent on the base 10. Continuing in that same way, this is log of 10 to the negative 4th power, and so the result is negative 4. Well, sometimes we want to evaluate a common log of a number that cannot be simply written as a power of 10, in which case we can use a calculator, because the common log is a button on a calculator. Here's what we want to do. First of all, we're going to use a calculator to find log of 32. So on your calculator keypad, there is a log button, and then put in the argument, or the number 32, and push enter, and we get 1.505 and so forth. A way to check this and a way to understand this particular logarithm is to evaluate on your calculator 10 to the result of that previous calculation, 1.505149978. Notice that that number is just about 32, or for all practical purposes, 32. Well, the other calculation we want to do is find log of 1/13. Again, using a calculator, log of 1 divided by 13 is equal to negative 0.1139 and so forth. To check this, we would want to do 10 to that power, which is negative 1.113943352. And we get a decimal. That decimal should be pretty close to 1/13. So let's compare it to 1/13 by just finding 1 divided by 13. And that is just about the number we got from the previous calculation. Well, continuing with our discussion of logarithms, there's some inverse properties that we'd like to be able to use. The following inverse properties hold for the common log. Log 10 to the x equals x. For any real number x. We've actually used that one a few times. But also we have this inverse property, 10 to the log x is equal to x for any positive number x. Well, with those properties in mind, we can solve equations involving bases of 10. Here's what we want to do. We want to solve the equation 3 times 10 to the negative 2x equals 15. The first thing to do is to isolate this exponential piece, so I'm going to divide each side by 3. So I get 10 to the 2x equals 5. Now, using that first inverse property, I know that log of 10 to some power will just be that power. So I want to take the logarithm base 10, the common log of the left, but I have to do the same thing to each side of the equation. So I'm going to take the common log of each side of this equation, so that applying the first inverse property, the left side simplifies to just negative 2x. And since I'm trying to solve for x, I now divide by negative 2, and I see x is log 5 divided by negative 2. Let's go to our calculator to get that result. We'll find log 5, close parentheses, divided by negative 2. That's negative 0.349 and so forth. Let's say that our answer is approximately negative 0.349. I'd like you to try a problem like that. Here's what I'd like you to do. I'd like you to solve the equation negative 6 times 10 to the x over 4 power equals negative 36. Stop the tape and try this one, and then restart when you're ready to check your work. Well, let's see how you did. As with the previous example, we're going to begin by dividing each side of the equation by negative 6. So I have 10 to the x over 4 equals 6. And now I'm going to find the common log of each side. Log 10 to the x over 4 is log 6. And then using the inverse property, I can simplify the left to x over 4, still equal to log 6. And finally, to get x by itself, I'm going to multiply by 4. So x is 4 log 6. Well, let's go to a calculator and get a decimal for that. We want to do 4 log 6, close parentheses. And that's about 3.113 if we were to round. So we can say that the solution to our equation is approximately 3.113. Well, let's continue our discussion of logarithms and look at logarithms of other bases. The logarithm with base a of a positive number x, denoted by log base a of x, this is a subscript, is defined by log base a of x equals k if and only if x is a to the k power. Notice that x is the argument, or the thing inside the logarithm. A is the base, the subscript, and k is the exponent on a that will give us x. Specifically, we need a to be greater than 0 and not equal to 1, and k can be any real number. When I put that logarithm into function notation, we call that the logarithmic function with base a. Well, let's pay special attention to this line for a minute and practice taking a logarithmic statement and writing it with an equivalent exponential statement. Here's what we're going to do. Suppose log base 2 of 8 is 3. This is equivalent to the statement 2 to the third power is equal to 8. Notice the base of the logarithm is 2, the base of the exponential statement is 2. The argument of the logarithm is 8. The thing inside the logarithm is 8. And that the number on the other side of the equal sign from the logarithm is the exponent on 2 that gives us 8. A log equals an exponent. With that idea in mind, this logarithmic statement read log base 16 of 4 equals 1/2 can be written 16 to the 1/2 power equals 4. Again, the log equals the exponent. The exponent is a power on 16 that gives us 4. Now in this third example, we're given an exponential statement and asked to write a log, or we're going to write a log statement. The base in this exponential statement is e. The log that goes with that is called the natural log, and the symbols for it are an L and an N. Now inside the logarithm, I put this decimal, 7.389, and the log has to equal the exponent 2. Again, this is called the natural log, and its base is the exponential base e. Well, let's work with that function just a little bit and do some graphing. What we want to do is graph the inverse functions, e to the x, that's an exponential function base e, and natural log of x, which is the logarithmic function. So let's go to our calculator and enter each function. We're going to put in e to the x power as y1, and then we're going to put in the natural log of x, and you can find that on your keypad also. Let's set a window of -5 to 5 in the x direction and a -5 to 5 in the y direction, and push graph. The first graph is the familiar exponential growth with base e. The second graph is the inverse function of that, the natural log of x. And you should recognize those, or they should look like inverse functions to you from your previous work with inverse functions. Well, now that we know those two are inverse functions, let's solve an equation that has a natural log in it. Remember those properties of logarithms and inverse functions. Here's what we're going to do. We want to solve the equation 5 times the natural log of x minus 1 equals 6. Our first goal is going to be to get this natural log of x by itself on the left. So I'll start by adding 1. 5 natural log of x is 7. Then divide by 5. So I'm at the point where I have natural log of x is 7/5. I want to know what is x. So I apply the inverse function to the natural log, and that's the exponential function base e. The way that it's applied is I write each side as a power of the base e. And again, I'm using e because it is the base of that logarithmic function. What happens on the left is that e to the ln x simplifies to x. And to find the value of x, we'll have to go to a calculator and figure out what is e to the 7/5. So let's do that now. We want e to the parentheses, that's too many parentheses, 7 divided by 5 power, and we get 4.055 and so forth. Let's approximate that to 3 decimal places and say that x is about 4.055. Let's continue with logarithms and look at a model. The table below lists the number of species of birds on islands of different sizes near New Guinea. And what we see in the table are square mile areas for different islands, 0.1 square miles, 1 square mile, and so forth. And this is the number of species of birds, 26 species, 39 species, and so forth. The first thing we want to do with this information is find values for a and b so that this model, f of x equal a plus b log x, this is that common logarithm, models the data. What we're going to do is take some data from that table, substitute it into the function to figure out a and b. So here's our model, or our function, f of x equals a plus b to the b times log x. You can use whatever data you like, but certain pieces of data are going to be advantageous. For example, if I use the data 1, 39 and substitute 1 for x and 39 for f of x, what happens is I get 39 is a plus b times log 1. Well, if you use a calculator and evaluate log 1, you'll find that its value is 0. Or you could think about it, what it's saying is, what exponent do you attach to 10 to get the number 1? And you know that 10 to the 0 is 1. So this term drops to 0, and I immediately know that a is 39. But I still need to know b. So go back to your table and pick any other ordered pair. For example, you might use 10, 52. Now I know that a is 39. What I'm going to do is put 52 for f, 39 for a. I don't know b, but I'll put 10 for x. And now I need to simplify again. And you can use a calculator, but you also know, or perhaps you're catching on to the fact that log base 10 of 10 is asking for what exponent on 10 gives me 10. Well, that number has to be 1. So we see that 52 is 39 plus b times 1. And all I have to do is subtract 39 from 52 to get b is 13. So my model is 39 plus 13 log x. Well, there's another part to this example, so let's continue. What we want to do is determine symbolically and graphically the island size that might have 50 different species of birds. Well, let's see. Our model now is f of x is 39 plus 13 log x. And we want 50 different species of birds. X is actually the island size, and f of x is the number of species. So symbolically, what we're going to do, is not put 15 for x, but put 50 for x. 50 equals 39 plus 13 log x. And we need to know x. So let's start by subtracting 39, and we get 39 from 50 is 11, is 13 log x. Divide by 13, and now I have to figure out how to solve for x. Remember that we can apply the inverse function, or use an inverse property of this logarithm. This is a log base 10, so I can consider each side a power of the number, or the exponential base, 10. And what happens on the right-hand side is 10 to the log base 10 of x simplifies to x. And so x is 10 to the 11/13th power. Well, let's see what number that is using a calculator. So we want to do 10 to the parentheses 11 divided by 13, and that's 7.017 and so forth. Let's just simplify that to 7. And we can say that x is pretty close to 7, and the units on x were square miles. What that means is there will be 50 species of birds, according to our data, on an island of size 7 square miles. Well, we also were directed in this problem to support that answer graphically. So let's see if we can support what we just did with a graphical solution. So we'll go to our calculator, and we'll graph the function, which is 39 plus 13 log x. And as a second function, we have a couple of choices. Let's, as our second function, put in 50 and set a window of something like 1 to 15 with a scale of 1 in the x direction, and 0 to 70 with a scale of 10 in the y direction. So I should see each of those functions graphed. Here's the model, 39 plus 13 log x, and there's the f of x equal 50. What I'm interested in is that point of intersection, and I want it to compare with what I did symbolically. So I go to second calc, option 5, and yes, that's good as a first curve. There's a fine second curve. Let's move our cursor just a little bit closer to the point of intersection and push enter. And we see that x is just about 7 when y is 50, and that verifies what we did symbolically. Well, in this lesson, we've done a number of things with logarithmic functions. Be sure to work lots of exercises from your textbook for practice.